Hey guys, welcome back. And today we'll be focusing on Task 2 of the Data Science Internship Program, which is offered by the Sparks Foundation. In Task 2, we'll try to understand prediction using unsupervised machine learning. And to go about this task, we are provided with the iris dataset, where our ultimate goal is to predict the optimum number of clusters and represent them visually. Now, this iris dataset is considered the hello world when it comes to unsupervised learning. So, in order to go forward into advanced datasets of unsupervised learning datasets, this is a very good place to start. Now, before we go further into the code as such, let's try to understand what clustering is. Now, consider a situation where you are trying to learn about something. Say music. One approach might be to look for meaningful groups or collections. Now you might organize your music by genre, while your friend might organize them by decade. How you as a person choose to group items helps you to understand more about them as individual pieces of music. Even in machine learning, we often group examples as a first step to understand our dataset. Now, grouping unlabeled examples is what is called as clustering. If the dataset is unlabeled, then clustering relies on unsupervised machine learning. And if the examples are labeled, then clustering becomes classification. Now, I think that's enough of an introduction into what clustering is. So let's go into our code. Initially, we'll be importing the relevant packages such as matplotlib and cbond for visualization, numpy and pandas for data manipulation, the typical packages like math, time, random, and datetime. Also, we'll be importing the warnings package. Now, this is just so that if there are any warnings, it does not make our code look kind of vague or something like that. Now, like I said, the objective is to predict the optimum number of clusters for the iris data. Now, initially we'll be loading our required data. Now, I have downloaded the iris dataset as CSV format, but you can also rely on the scikit-learn package because the iris dataset is a preloaded dataset on the scikit-learn. Now, iris.data is where you have your independent features, and iris.target is where you have your target variable. Now, I know what you're thinking. If this is an unsupervised learning algorithm, then why do we have a target variable? Well, iris dataset is basically you can do both clustering as well as classification on them. So this is a perfect example where you can practice your classification skills as well as you can learn or practice your clustering skills. Now let's view our dataset that we have imported. Now we have 6 columns where one is ID, the other is sepal length, sepal width, petal length, petal width, and finally we have our species. Now from this, our main goal is to use these 4 columns and cluster them with respect to the species. Since the ID column does not play a major role, we'll be dropping them using the .drop function. Next, we'll be splitting our dataset into features, which is our independent variable, and label, which is our target variable or dependent variable. Now, I've used the ilog function. You can definitely use many other methods. With the ilog function, what I've specified is first, I'll consider all the rows. Then I'll consider all the columns except the last one. -1 refers for the last one. That's when it comes to features. When it comes to labels, I'll be using again the ilog where I taken all the rows, but I'll only concentrate on the last column, which is our species. Now let's understand about the dimensionality of our dataset. Now we have, for our features data, we have 150 rows and 4 columns, and we know those 4 columns. Whereas for our label data, we have 150 rows, and we have only basically the species column. That's all that we have. Now, even though the dataset is small and even though the dataset is easy, we will still be doing data analysis because that's one major important thing in any data scientist's life. So before I usually do my data analysis, even there I specify the problem so that when someone else is going through the code, they understand what the problem is, and that's our main objective that we're trying to solve. We'll first use the describe function to understand or get a description about the data. Now we have the first quartile, which is the 25th percentile, 50th percentile, and 75th percentile, which is the third quartile. And we see that the values are not that far from each other, which is a good thing. Now we'll check for the missing values, and we'll first use .info, and we'll see we have 150 non-null. Again, we have another 150 non-null. All the rows are there, which means there are no null values. But then again, a picture is worth 1,000 words. So let's see how they are when we plot them. We'll use the Seaborn library this time. And when we see there are no missing values, which is a good thing. So we can go forward. Now we'll be using the pair plots. Now pair plot basically gives you an understanding between multiple features. So it's like or not multiple, maybe you can say bivariate analysis, perfect for bivariate analysis, what a pair plot is. Now here you can see your density plots, and here you can see your scatter diagrams. Now in all these scatter diagrams, if you notice one thing, you can see that your Certosa, that is your first one of your species, they are always separate from each other. In all the cases, they are on their separate group. And you can see a bit of clustering here. Now, like I said, here we are trying to understand if we can differentiate the species even before we go into prediction. And we can actually. If you're looking at it, Certosa is a group. Here you can see Versicula is a group and Virginica is a group. You can definitely differentiate them. Now we'll get into what clustering is. Now we'll be using the K-means clustering. Now the idea of K-means clustering is that we specify the number of clusters. We actually pre-specify the number of clusters. Now rather than going into that, let's understand the elbow plot now. This is a very important plot, guys. With this, you can actually estimate your number of clusters. We'll be looking more or less at the sum of squares of error, which is SSE. And we keep a range from 1 to 10. You can definitely keep much more, but we'll keep a 1 to 10 because we know it's 3 because there are only 3 species in our group. So the ideal number of clusters is basically 3. That's why we're keeping from 1 to 10. Then we'll be running this for loop, which will append all the K values or K range values into SSE. Then we'll be plotting these, and then we can see that at 3 there is an elbow. Now these are our K values, sum of squares of error. Now how do we say that this 3 is apt? So we say that the cluster is basically 3 because here you can see after 3, the sum of squares of error does not decrease significantly with every iteration. It's reducing slowly, but here from 2 to 3 there's a drastic change. From 1 to 2 there's a drastic change. So because of that, we'll say K equal to 3 is the perfect or the optimal number of clusters. Now we'll go for a visual representation of these optimum clusters. So we'll keep them as n clusters equal to 3. K-means is our algorithm that we are going to focus on. We'll use the fit underscore predict, where you fit and predict at the same time rather than just fitting and then predicting. We'll use the fit underscore predict. And we can see one thing. We can see the 1, 1, 1, all there are ones. Then we can see a few zeros, but there's a 2 here. So there are a few misclassifications as well. It basically happens in iris data, so there is a bit of misclassification. You'll be able to visualize them. Now, before we check for our results, we'll see how much of these values are there. Now, we see that Virginica is 50, Versicolor is 50, and Certosa is 50. So we know that there are 50 values as such. Next, we'll be comparing our actual value versus the predicted value. Now, on your first column, these columns are your actual values. And these 0, 1, 2, 1 and 2 are your predicted values, which is your y underscore k means that you've predicted right above. Now what you can see is Iris setosa, they have labeled 50 of them as 1. When it should have been 0, they have been labeled as 1. Iris versicolor has labeled 48 as 0. Now this is fine because see, it's a transpose of each other. Setosa has labeled 50 as 1 and versicolor has labeled 48. Versicolor should have been 1, but they have labeled 48 as 0. But there are 2, which is a misclassification. So that is not right. In Virginica also you can see that 36 have been classified correctly or clustered correctly, and 14 of them are not correct. They have been mislabeled. Now let's understand a bit more with visualization. Now I've used this code here. It might look big, but it's actually very easy to understand. This is basically the figure size. We don't need to dwell much into that. This is the subplot 1 that we're giving, subplot 2 that we're giving. This is basically a title, the X label, Y label, the legend, that's all. Now, these 4 are basically your scatter plots. The first scatter plot will represent your iris setosa values that has 0 and 1. Second, iris versicolor, and third, iris virginica. Now, these 0 and 1, they represent your sepal length and sepal width. Now, the scatter plot will be here focusing on the cluster centers, the centroids. In this case, we look for the sepal length centroid and the sepal width centroid. And when we can view them, similarly, this is for the predicted value. The above one is for the original, and this is for the predicted ones. Now, when we view them, we can see that they're somewhat same. You can see here in the actual one, you had the iris setosa labeled here. But we have came to know that iris setosa has been classified as in the position of 1. We've seen that in our crosstab. We have seen 50 of them have been clustered as 1, whereas in versicolor 48 have been clustered as 0. So here we can see versicolor in the place where setosa was there, versicolor has taken place. Similarly, where blue, which is versicolor, was initially there, red, that is setosa, has been there in our predicted value. Virginica does not have much because we know that 36 of them have been correctly clustered. So 36 of them are right here, although there are a few, 14 have been misclassified, and we know that. Now that is with respect to sepal length and sepal width. Now let's look into petal length and width. Now here we look at the figure size, then we can see the subplot, same thing. Only here, when it comes to petal length and width, we look at 2 and 3. Now, why 2 and 3? If you're looking at our data set on top, I'll just take you there. You can see 0 represents sepal length. 1 represents the index value, column index value. 1 represents your width. 2 represents petal length and 3 represents your petal width as well. Okay, now let's just get back to where we were. Okay, we'll be doing the exact same thing, and we can see the following thing. We can see setosa has been interchanged with versicolor, and versicolor has been interchanged with setosa when it comes to actual and predicted. But then again, your petal, all this are somewhat similar. So we can say that this 3 is actually the optimal number of clusters that is required, and we have actually shown them. We have basically completed our task by showing on how we can view them visually. Thank you.